In this video, I'd like to go over some problems from Chapter 5 involving the ideal gas law and derivations of the ideal gas law. So we'll start with some examples of the ideal gas laws, Boyle's law, Charle's law, and Avogadro's law. And we saw in class how to deal with these from the derived universal gas law. So we're going to take a look at how to actually work with that derivation and how to come up with these laws on the fly. So how do we get Boyle's law from the universal gas law? So if we look at the first one, it says a sample of CO2 occupies a volume of 20 liters at 23 degrees Celsius and 1 atmosphere. Calculate the volume of the sample at 23 degrees Celsius and 0.830 atmospheres. Now, the way that I like to start all of these problems is to kind of write down what we know. So we have a pressure, we have a volume, and a temperature of a gas sample. So in this case, the pressure initially was 1 atmosphere. We have a volume of 20 liters, and we have a temperature of 23 degrees Celsius. So we kind of get that down to start. And then we change some things. So in this case, we're changing the pressure. It wants to know what the volume is, so we're going to put a question mark for that. And this is in the second case. And the temperature, that's going to remain constant. So just from this set of variables, we know that we have Boyle's law because the temperature is constant, so we're going to wind up eliminating that. And we're not changing the number of moles, so that's also going to be a constant. So if we write down the universal gas law, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, we can start to eliminate some things. One of our constants is temperature. That's not changing. We know the number of moles is not changing because it's the same exact sample of gas, so this would be like a gas inside of a balloon. So what we're left with is P1 V1 equals P2 V2. So in this case, if we just write down P1 V1 is equal to P2 V2, we can start to plug in some of the things that we know. So we have 1.00 atmospheres is where we started. We have 20.0 liters, and this is going to equal 0.830 atmospheres times volume 2, which we don't know. So if you solve for volume 2, you're going to get 24.1 liters. And this makes sense because if you think about it, what we've done is we've reduced the external pressure. So we went from 1 atmosphere to 0.830 atmospheres. So remember, gases have this effect where the molecules hitting on their container, in this case this would be something like a balloon, exert a force. So we have the force of the molecules inside the balloon competing with the force of the molecules pushing down on the balloon from the outside. So the air inside the balloon versus the air outside the balloon. If we lower the outside pressure, what's happening is the force that's being applied by the molecules outside the balloon is going to go down just a little bit. So that means that the molecules inside the balloon can start to push against those outside molecules, causing the balloon to expand. So what we wind up getting is a slightly larger volume, which makes sense with Boyle's law, which shows an inverse proportionality between pressure and volume. So with the second one, we're going to look at how we do this with Charle's law. So in this case, it says a sample of oxygen occupies a pressure, volume, and temperature. We're going to write those down. So it says that a sample of O2 occupies a volume of 4.38 decimeters cubed. We'll talk about that unit in just a second. At a temperature of 19 degrees Celsius and a pressure of 101 kPa. And then it says, what happens if we keep the pressure the same? So this thing says 101 kPa. We change the temperature a little bit. We go from 19 to 25 degrees Celsius, so we heat it up. What's going to be our new volume? So in this case, the pressure is the constant, so that's going to wind up dropping out. Again, like in the previous example, we are not changing the number of moles. That's staying the same. So what we're changing is just the temperature and seeing what happens to the volume. Now, you may notice this odd unit of decimeters cubed. If you remember back to when we were talking about units in chapter 1, a decimeter cubed is actually a liter. So that actually makes life a little easier. It's just another way of saying liter. And then we have to deal with these temperatures. Now, whenever we're doing anything with the gas constants, we have to convert this to Kelvin. We need to be on an absolute scale. So we have to add 273.15 to each one of these in order to work with them. And you'll see in a second why this is actually important. So this gives us 292.15 Kelvin for this one, and this gives us 298.15 Kelvin for this one. So if we do P1 V1 is equal to, over N1 T1 is equal to P2 V2 over N2 T2, what's going to cancel out in this case is the pressures. Those are the same. The number of moles are the same. So we get V1 over T1 is equal to V2 over T2. That's Charle's law. It's a direct proportionality in this case. So if we plug in, we're going to get 4.38 liters is our volume 1, divided by temperature 1, which is 292.15 Kelvin. And then this is going to equal our V2, which we don't know, divided by 298.15 Kelvin. And then if we solve for V2, we're going to get 4.47 liters. Oops. We're going to get 4.47 liters. So again, we should ask ourselves, does this make sense? Does increasing the temperature, should that lead to a slight increase in the volume? And the answer is yes, it should. If you increase temperature, if we go back to the molecules in the balloon, increasing the temperature is going to cause them to speed up a little bit. If they speed up a little bit, they're going to hit the walls a little harder, which means that they're going to start to be able to push out against the force of the molecules pushing down, leading to the balloon being able to grow a little bit in size. So this increase in volume is actually consistent not only with the physical picture, but also with this direct proportionality that we have with Charle's law. So now the last one is an interesting one. This is Avogadro's law, and it's Avogadro's law. We talked about it a little bit in class, but to give you a sense of how this might be used, Avogadro's law basically says that the volume is proportional to the number of moles. So the volume of a gas is proportional to the number of moles. And that makes sense because from PV equals nRT, we can get volume on one side and the number of moles along with RT over P on the other. So if we use this for a reaction, what that basically means is that if we have a 1 mole of N2 is proportional to 3 moles of H2, meaning that if we react 1 mole of N2, we're going to need 3 moles of H2, we can say that 1 liter of N2 would require 3 liters of H2 because volume is proportional to the number of moles. So in this case, it asks us to calculate the number of liters of H2 necessary to produce 49 liters of NH3. So instead of using stoichiometry, we can actually use this proportionality that volume is proportional to the number of moles under the same conditions, which in this case it is because the reaction is taking place at the same temperature, is taking place at the same pressure. These gas molecules are mixed together. So they all have the same pressure and temperature. So we can use this relationship of moles to liters to give us a leg up in the stoichiometry. So we have 49.0 liters of NH3. And in this case, our relationship here is that for every 1 liter of NH3, we would need 3 liters of H2. So we can say that based on the stoichiometry, 49 liters of NH3 would require 147 liters of H2 from the 1-to-3 ratio in the reaction. So Avogadro's law is basically this concept that volume is proportional to the number of moles. And we can then extend that to the stoichiometry of a reaction. In the second lecture problem, we're going to look at how to use PV equals nRT to start analyzing things related to reactions. Now, in this particular instance, we're not going to have to involve stoichiometry. This one is a simple sort of plug and chug kind of approach to PV equals nRT. You're going to see that we're going to be given some information. We're going to be given a volume, a pressure, and a temperature. And it's going to ask us to calculate the number of moles, which we then use to get the number of grams. In a later slide, we're actually going to look at how we can use PV equals nRT to work with stoichiometry. So in this case, it says the decomposition reaction for potassium chlorate is 2KClO3 gives 2KCl plus 3O2. And then it says, calculate how many grams of O2 were produced if the gas occupies a volume of 1.23 liters at a pressure of 750.2 torr and a temperature of 21 degrees Celsius. So in this case, what we're going to do is we're going to start by just writing down the information that's given. So we're given a pressure, which is equal to 750.2 torr. And I recommend automatically converting this to atmospheres. We know that there are 760 torr for every 1 atmosphere. So in this case, that's going to give us 0.9871 atmospheres. They give us a volume of 1.23 liters. That's fine. We can use that as is. And they give us a temperature is equal to 21 degrees Celsius. So we're going to automatically convert this by adding 273.15 to Kelvin, which gives us 294.15 Kelvin. And in this case, it wants to get the number of grams. So to get the number of grams, we need to get the number of moles. So we can set up PV equals nRT. And to get the moles by itself, we can divide both sides by RT. And then we can say that N is equal to PV over RT. So if we plug in the variables for this, we get 0.9871 atmospheres is our pressure. Our volume was 1.23 liters. The gas constant is 0.0821 liters atmospheres per mole Kelvin. And then our temperature was 294.15 Kelvin. So if you calculate the value for N, you get 0.05027 moles of O2, which we can then convert to a mass by knowing that for every 1 mole of O2, there are 32 grams, which is going to give us 1.609 grams of oxygen. Now, it is important to recognize that in this case, O2 has 2 oxygen atoms, so the molecular weight is 32 grams, not 16. So we have to make sure that we calculate for the O2, not just for O. That's a common mistake that happens. So then in the second part, this just asks for a percent composition. So calculate the percent of oxygen in KClO3 if the initial sample weighed 2.052 grams. So we know that percent composition of oxygen is going to equal the mass of the oxygen divided by the mass of the sample times 100. So in this case, we got the mass of the oxygen was 1.609 grams. Divide that by the mass of the sample, which is 2.052 grams. We multiply that by 100, and we get 78.4% is the percent of oxygen in that sample. So as you can see here, we didn't have to use stoichiometry. We were able to calculate these values just from getting the number of moles in the mass, and then subsequently remembering what percent composition was. But this can show you how PV equals nRT can be useful in interpreting things related to reactions. Now, in the second part of this, we're going to be working with the ideal gas law, but looking at one of the interesting derivations that we can get from the ideal gas law, which is density. So if you remember from class, PV is equal to nRT. And we can go back to our chapter 1 information where we have mass over molecular weight is equal to the number of moles. So if you take, for example, 15 grams and divide it by the molecular weight of whatever it is, like for example, CO2 would be 44 grams per mole, that's how we would get the number of moles. Now, if you plug this in for the number of moles up here, we get PV is equal to M over molecular weight times RT. And then we can sort of rearrange things to get a density. So if we reorganize this such that we bring the molecular weight up, so P molecular weight is equal to M over V. We basically bring the molecular weight up and the volume down. Over RT. We recognize that mass over a volume is the same thing as density. So from this, we can get that P molecular weight is equal to density times RT. And then if we get that the density by itself, density is equal to P molecular weight over RT. So from knowing what the moles is, basically it's a mass over molecular weight, plugging in and reorganizing like we did in class, you can see that we can derive an equation for density, where density is equal to P molecular weight over RT. So following this equation, what we can say in this particular instance, we can say that the density, which is 2.26 grams per liter, is going to equal the pressure, which in this case is 0.862 atmospheres, times the molecular weight, which is what we're interested in, divided by R, which is 0.0821 liters atmospheres per mole Kelvin, times the temperature, which is 25 degrees Celsius plus 273.15. Again, we have to convert the 25 degrees Celsius to Kelvin, so we add 273.15. If you solve this for the molecular weight, you're going to get a molecular weight of 64.17 grams per mole. So this, you could either memorize this, meaning that you can memorize D is equal to P molecular weight over RT, or even better, if you know how to derive it, you can derive the density expression or the molecular weight expression, both of which will give you both of which will be important for the exam. You have to know how to do this. On this slide, we're gonna look at how we can use the gas law in terms of stoichiometry. So how can we relate what we're doing in chapter 5 back to what we were doing in chapter 3? So in chapter 3, we had created this little chart that says that we can get from moles and we can go between moles and mass using the molecular weight, and we can go between moles and the number of things using Avogadro's number. Well, we can add in two new spokes to this. We can add in for a solution volume, for example. We can use concentration, so that allows us to go between moles and the volume of a solution. And now we have pressure, volume, and temperature. We can use the ideal gas law. So for this spoke, we can use PV equals nRT. So we can get from any one of these external points, mass, pressure, volume, temperature, volume, or the number of things, we can get to moles and then get to any one of these other parameters as long as we have enough information. As long as we have a concentration, we have the variables pressure, volume, and temperature, or whatever combination we would need to get to moles, we can calculate anything we want. So knowing this, this is very powerful. And then if we add on to this the fact that we have coefficients in a balanced reaction, we can go from moles of one thing to moles of another. So we're actually going to see that in the following expressions. So in the following questions. So in question number 1, it asks us, how many liters of Cl2 can be obtained, and it gives us a temperature and a pressure, so for the reaction, from 9.41 grams of HCl. So we have a mass of HCl, which we're going to start with, and then it wants to know, what's the volume of Cl2 that can be produced. So from mass, we know we can get to moles of HCl using the molecular weight. If we want to get from moles of HCl to moles of Cl2, we can use the coefficients. And then finally, we can go to volume using PV equals nRT. So this is actually a very powerful process, because knowing this very simple diagram, we can go anywhere we want in chapters 3, 4, or 5. We can do limiting reagent problems. We can do whatever we want. So for this problem, we're going to start with our 9.41 grams of HCl. We have our molecular weight, which is 36.46 grams for every 1 mole of HCl. And then our stoichiometry is that there are 16 moles of HCl for every 5 moles of Cl2. I pulled that right from the balanced equation. So from that, we can get 0.08079 moles of Cl2. Now, the reason why I want moles is because in PV is equal to nRT, we need to have the number of moles in order to work with it. So we don't have to go on to a mass, because we can just use the number of moles in this case. So the variables that were given that relate to PV equals nRT is the temperature, which is equal to 40 degrees Celsius. We automatically add 273.15 to get Kelvin, which is 313.15 Kelvin. The pressure that's given to us is 787 millimeters of mercury. We're going to automatically convert that to atmospheres. And this gives us 1.035 atmospheres. And so then we have then we have everything we need in order to solve PV equals nRT. So I like to get the variable I'm solving for all by itself. So in this case, volume is equal to the number of moles times the gas constant times the temperature divided by pressure. I do that by dividing both sides by P. And so in this case, we're going to have the number of moles, which we calculated, 0.08079 moles, times the gas constant, 0.0821 liters atmospheres per mole Kelvin. Our temperature, which is 313.15 Kelvin. Sorry, that's a little crushed up against the edge there. Just so that you guys know, this is 313.15 Kelvin going over there. We divide by the pressure, which is 1.035 atmospheres. And from this, we can get that the volume is equal to 2.00 liters when you calculate for the volume. So in this case, using stoichiometry becomes quite simple as long as you understand that the step going into or out of the equation might just be PV equals nRT. So in the second one, we're gonna basically go in the reverse direction. We're given a volume of NH3 and some information about it, that it's at 0 degrees Celsius and 1 atmosphere. And then it wants us to use our stoichiometry to get the mass of Mg3N2. So we're given a volume of NH3. We're going to convert this to the number of moles of NH3 using PV is equal to nRT. We can then get the number of moles of magnesium nitride using the coefficients. And then finally, we're going to get the mass using the molecular weight. So in this case, you'll notice that we're given the temperature is equal to 0 degrees Celsius, and the pressure is equal to 1.00 atmospheres, and the volume is equal to 5.85 liters. And we want to get the number of moles. Well, you can kind of do this the hard way, which would be to convert this, so add 273.15. And then you have PV is equal to nRT. And then you can solve for the number of moles by plugging everything in. Now, if you looked at this, the 0 degrees Celsius and 1 atmosphere may be a recognized set of conditions. In this case, we're at STP. So STP is defined as being 0 degrees Celsius and 1 atmosphere. So since we're at STP, we know that 1 mole of a gas is equal to 22.4 liters. So if you recognize that, you can save some time and use this relationship that 1 mole is equal to 22.4 liters. You can only do that at STP, or at 0 degrees Celsius and 1 atmosphere. I'm going to do that in this case just to show you, how that makes life a little bit easier. But if you didn't recognize that, you are perfectly welcome to use PV equals nRT to calculate it. You're going to get the exact same number. You're going to get full credit on the exam. But this may save you some time if you can recognize that it's at STP. So we're going to start with our 5.85 liters of the NH3. We're going to use our STP relationship that there are 22.4 liters for every 1 mole. Now that we're in moles, we can use our coefficients. So for every 2 moles of NH3, there is 1 mole of Mg3 and 2. And then finally, we want to get our mass. So for every 1 mole of Mg3 and 2, there is a molecular weight of 100.9 grams. So at the very end here, guys, you're going to get a mass of 13.2 grams of Mg3 and 2. And that's again coming from the stoichiometry and the coefficients. In this case, the only thing that might help you a little bit is to be on the lookout for STP, which may help you to save a few steps rather than using PV equals nRT.